Welcome to the beginning of Chapter 3 about systems of equations and matrices. This first section is going to be a review of the 3 ways that you already know of how to solve systems of equations. Actually, they put 4 different ways into this section, one of them that we haven't used very much, and then 3 other ways that you guys have seen multiple times before. So we're going to talk about today how to solve them graphically and how to solve systems algebraically, which is by substitution and elimination. Hopefully that rings a bell. The vocabulary you should be looking for in this section are these words and phrases: the break-even point, a system of equations, consistent, inconsistent, independent, dependent, and then the 2 algebraic methods that you know from Algebra 1 and hopefully from review in geometry: substitution and elimination. All right, when we talk about a break-even point, what we mean is the point at which, in this case, income is equal to cost. So in this particular example, someone named Libby is borrowing $450 to start a lawn mowing business. So she starts owing $450, right? And then she charges $35 per lawn and incurs $8 in operating costs per lawn. A system of equations can be used to determine the break-even point. So at what point is how much is she spending equal to how much she's making, right? And if you're running a business, you want your income to exceed your costs. So you'd want to be up here in this piece of the line. When you're down here at any point here, your income is lower than your cost. And we can use a system of equations to find what we call the break-even point, which is where those 2 lines intersect and they are equal. A system of equations, remember, is 2 or more equations. In this chapter, we'll learn how to do systems with 3 equations and 3 variables, but today we're just going to be working with 2 equations that have the same variables, and we need to find the ordered pair that's true for both equations. So if we look at this graph, there's only one ordered pair that's on both of the lines, and that's this ordered pair here, which is the break-even cost. After she does 16.7 lawns, her income and her cost would both be equal. So she would be making 0 but losing 0. Beyond that, her income would be greater than her cost. All right, the first method they're going to show us here is to solve by using a table. I did include this on your notes. This is the first example. This is not something we focused much on in Algebra 1, but I'm just going to show you what they mean. So here's my system of equations, 2 equations that I need to solve together. So I need an x and a y that make both of these equations true. So I'm going to set each equation equal to y, just to make it a little bit easier to make a table. So here's my first equation, y equals negative x plus 3, and my second equation is y equals 2x minus 6. So I'm going to set up a table where I'm going to plug the same x values, 1, 2, and 3, into both equations. So if I plug x equals 1 into the first equation, I get 2. If I plug x equals 1 into my second equation, I get negative 4. Those 2 ordered pairs are not the same, right? So that would not be the point that satisfies both equations. If I plug in x equals 2, I get the ordered pair 2, 1 from the first equation. You can see that here. If I plug in 2 to the second equation, I get negative 2. Again, those do not give me the same thing. But when I plug in 3, if I plug in 3 to the first equation, I get 0. And if I plug in 3 to the second equation, I also get 0. So notice I get the same ordered pair for both equations. That means that that ordered pair is the solution. It works for both equations. So what I would like you to do is to try this one using a table and see if you can find the solution. All right, hopefully you answered B. If you have a question about that one, we can talk about it in class tomorrow. All right, solving by graphing. This is a method that we learned in Algebra 1. This is when you graph both of the equations on the same graph and you look for where they intersect. Their intersection point is also their solution. It's usually easier to start by rearranging both equations in slope-intercept form, so y equals. So here I move my x to the left and then divide by negative 2, and I get y equals 1/2 x. For my second equation, I subtract x from both sides, and I get y equals negative x plus 6. And then I'm going to graph both of them. So if you take a look at this graph, this is my first equation. Notice there's nothing added to my x term, so that's like having a y-intercept of 0. And the slope of 1/2, I go up 1 and to the right 2, up 1 and to the right 2, up 1 and to the right 2. When you're solving systems by graphing, you need to graph as many points as will fit on the graph that you're working with, making your line as exact as possible. When we graph the second line, it has a y-intercept of +6 and a slope of -1. So I graph as many points going down 1 and to the right 1, down 1 and to the right 1 as I can fit on my graph. And then there will be one point that overlaps, which is right here. That is the only ordered pair that makes both equations true. So in this case, my solution is that point 4, 2. And we can always check by plugging in, these are my two original equations. We always check in the original equation. Remember that the ordered pair I'm checking is the ordered pair for 2. So I plug 4 in for x and 2 in for y, and they both work. If I plug 4 in for x and 2 for y in this equation, I get 0 equals 0, which is true. If I plug 4 for x and 2 for y in this equation, I get 6 equals 6, which is also true. So that means our solution is 4, 2. What I would like you to do now is try solving this system of equations by graphing. All right, you should have gotten A. Notice the solution here is 4, 1, and again, we would be able to check that in both equations to see if it worked. All right, here is some vocabulary that is probably a little bit new, but the concept is review. There are 3 things that can happen when we graph a linear system that has 2 lines or 2 equations in 2 variables. Both of my lines could have different slopes, and if both of my lines have different slopes, my lines will intersect and there will only be one solution. So if you want to make a note to yourself that these kind of lines have different slopes. The other thing that could happen is both of my lines could be exactly the same line. So when I solve them both for y, it turns out that they have the same slope and the same y-intercept. When that happens, every point that's on one line is also on the second line because both lines are exactly the same. That means we have infinitely many solutions, and you are allowed to abbreviate that as IMS. And inconsistent systems are parallel lines, so they have the same slope, but they have different y-intercepts. If they're parallel, they never touch, and so there's no ordered pair that they share, no solution. So the vocabulary that's new in this section is this. If my lines cross at one point, I say that my solution is consistent and independent, meaning there is a solution, but my lines are independent. They're 2 different lines. I can also have a system, this is when it's the same line, infinitely many solutions, that's consistent, meaning there are solutions, but it's dependent, meaning the lines depend on each other. They're the same line. Or if there's no solution, we say that my system is inconsistent. So we're going to graph 3 different examples here to see an example of each of these kinds of systems. So in this system, I'm going to solve each of my equations for y. You should know how to do that from what we looked at in Chapter 2. So notice here that my slopes are different. Here the slope is 1, here the slope is -1/2, so I should already expect it to be consistent and independent. When I graph, you will see that that is true. If I graph both of those lines, they cross at one point, and that point is 2, -3. So the solution is 2, -3, and the system is consistent and independent. You should graph these lines on your note guide. The second one, we have a system here, and again, we're going to solve each of those equations for y, and you'll notice here we get the exact same equation. So both of these equations represent the same line. So when I graph my line, it looks like I just have one line. So we say that the system is consistent and dependent. And we would say that this system has infinitely many solutions. Lastly, if I solve both of these equations for y, notice here I have the same slope of 5/2, but I have different y-intercepts. My y-intercept here is -5, and here is 0. So when I graph those, they're going to be parallel. The system is inconsistent, and we say that the system has no solution. There's no ordered pair on both lines. All right, try this one for me. Hopefully you answered A, consistent and independent. And let's do one more. This one is consistent and dependent. Okay, what we're going to do now is talk about the two algebraic methods that we have so far to solve systems of equations. The first one is called substitution. Substitution has 3 steps. Step 1, I pick one equation and I solve it for one of the variables. So I make it either y equals or x equals. Step 2 is to do the substituting. I substitute whatever I have here in for the variable in the second equation, solve it, and then step 3, I substitute to find my other variable. So let's look at an example of how this would work. We're going to look at this word problem, so take a second to pause and read it. All right, so what we're looking for here is how many of each chair were sold. Here we have 2 different kinds of chairs, so this is going to lend itself very well to a system of equations. My plan is I'm going to define my variables and write the system. So we're going to say, let x represent the number of rocking chairs that I sell, and y is going to represent the number of Adirondack chairs that we sell. So the total number of chairs sold was 48. The number of rocking chairs plus the number of Adirondack chairs altogether is 48. And then the other piece of information that they give is that our total amount of money is $13,930. $265 per rocking chair and $320 per Adirondack chair. So now I have a system of equations, 2 equations, 2 variables. I'm going to pick one of my equations to solve for a variable. If we look back here at my system, it's going to be easiest to pick this first one and get either x or y by itself. So that's what we're going to do here on this next slide. We're going to subtract y from both sides, and I'm going to get x by itself. So 48 minus y is equal to x. And then what I'm going to do with that, since I know that this is equal to x, 48 minus y, I'm going to plug that in wherever I see an x in my other equation. So I replace x with 48 minus y. Now I have one equation with one variable y. Then we solve that. You can pause if you need to take a second to follow the math all the way through, and we end up with y equals 22. Remember, y was the number of Adirondack chairs, right? 22 Adirondack chairs. Now that I know that y is 22, I can pick either one of my original equations. You should pick the easier one. Substitute 22 for y, and I get x equals 26. So that means I sold 26 rocking chairs, because rocking chairs was x, and 22 Adirondack chairs. All right, and you can always check. Here they're using a graphing calculator to show you that that solution works. I want you guys to try this one. And the answer is B, 120 adults, 210 children. If you're not sure about the setup, we can talk about that in class. All right, last but not least, we have the elimination method. Elimination is where I multiply one or both of my equations by a number so that I can get my x's or my y's to be exactly opposite. Then I add them so that I eliminate a variable, and then I solve and substitute. So let's look at this example here. I have x plus 2y equals 10 and x plus y equals 6. What I want to do is force one of my variables to cancel out. So I notice here I have 1x and 1x. Well, if I multiply this whole equation times -1, this equation becomes -1x minus y equals -6. Then if I leave my first equation the same, and then I add my 2 equations together, x plus -x is going to give me 0. 2y plus -y gives me 1y, and 10 plus -6 is 4, so I know y equals 4. Now I just need to pick one of my original equations to substitute in and solve for x. So if you follow the work I just did here, I substituted 4 in for y, and when I solve for x, I get 2. That means my final answer, which I'm going to write as an ordered pair, especially since this isn't a word problem, is 2, 4. So this would be the point on the graph where these 2 lines would cross. There's one solution here. Please try this one. Your answer is B. And I just want you to look at this last example, which